It's a good idea. Okay, so today is Tuesday, November 3rd. This is Math 265, Multivariable Calculus. And we're going to continue exploring how to convert integral problems that we don't really have a good sense of how to solve into different coordinate systems. Okay? So for instance, last week we saw how to take an integral, a function of two variables, and rewrite it in terms of polar coordinates, and to actually change the entire double integral, at least the iterated integral, so that it was easier to solve. So today we're going to just sort of draw a parallel between how we solved double integrals over type X regions and type Y regions. We're going to do that with polar coordinates, so we'll talk about, call them type theta regions. So remember, type X region meant that the Y coordinate was bounded by a function of X. And a type Y region said that the X was bounded by functions of Y. So type theta regions is where the R, because remember polar coordinates you have an R and a theta. It's where the R is going to be bounded by a function of theta. Okay. And then we'll talk about cylindrical coordinates. So we'll remember what those are and then see how to translate problems into that. And that's going to be quite easy. Because if you remember, cylindrical coordinates just look like polar coordinates, and then take the z part, this is for three-dimensional, take the z and rewrite it as z. So if xy became r theta, then xyz became r theta z. The z didn't change. Okay, and that'll probably be as much as we get to, but if we if we have time, then we'll also look at spherical coordinates again. But I suspect we'll probably only get through the first two. Okay. So let's look at type theta regions. Okay, so remember, when you're working in polar coordinates, you're looking for polar rectangles, and that's where the r is bounded by two numbers and the theta is bounded by two numbers. But the next best thing is going to be where the theta is going to be bounded by two numbers, and then the r is not bounded by two numbers but by two functions of theta. So it might look like all pairs r comma theta, where say alpha is less than or equal to theta is less than or equal to beta. And then r is going to be bounded by two functions of theta. So this is what a type theta region should look like. You have the rectangular part that is bounded by two numbers, and then over here it's bounded by two functions of theta, hence the type theta region. So what is this going to look like? Well, let's see. Let's draw a ray out at angle alpha and another ray at angle beta. Actually, since beta is bigger, the first one should be beta. So this whole thing is beta, and this little thing is alpha. So the region is going to go between alpha and beta. And then the radius, well, is a function of whatever your theta is. So maybe radius looks like that, and then here's a function like this. So this is g1 of theta, and this is g2 of theta. And since r has to sit in between them, that's the region that you're actually going after. Okay, so if you have this type of region, say this is your D, then we get a similar formula for how to integrate over it as we did for rectangular coordinates when we had type X or type Y regions. So if S is continuous, okay, remember the continuity condition is just telling us that our double integral is going to exist. If f is continuous on D, then the integral over d of f, dA, is the integral from alpha to beta, integral from g1 of theta to g2 of theta, f of r cosine theta. I can do a little better than that. R cosine theta, R sine theta, R dr d theta. Now I want you to remember, when I write the f over here without anything, I mean f of x comma y, for instance. I could put this in, this could be in rectangular coordinates. But we're changing to polar coordinates, and remember, when you change from rectangular to polar coordinates, x is r cosine theta, and y is r sine theta. So I'll just write that for you, so you remember it. X squared plus y squared is r squared. Tangent of theta is y over x. Okay, but this is the important thing. So you could, and this is exactly what we had for type x and type y regions. You could write down this iterated integral where you put functions in the top and the bottom. And also note this extra r out here, which was a consequence of changing the polar coordinates. We showed last time that that's what pops out. Okay. I'll give an example of this. So and actually here I'm going to start with a function that's, or a domain which is given by a polar function. So r equals cosine of 2 theta. And graphing these things takes a little bit of effort to learn how to graph them. But let's just start by plotting points a little bit and see what's going on. So if theta is 0, then r is cosine of 0. Cos is like cone, which means width, so that's cosine of 0 is 1. So when the angle is 0, then you have to go out radius 1. Okay. And from this we can clearly see that the graph is going to look like, nice little jokes. I drew one point and I said we can clearly see what the graph is going to do. Let's try another one. How about pi over 12? Why did I choose pi over 12? Yeah, when you multiply by 2, it becomes pi over 6. And cosine of pi over 6 is root 3 over 2, right? So pi over 12 is this angle coming out this way. And now we're not looking at the y-coordinate, right? We're looking at the radius, how far it is away. So if it's root 3 over 2, if this is 1 away, then it's probably like around there. So you see what's happening is it's starting to go up. But it's not going to go up forever. It's actually going to turn around. So let's see. At pi over 8, then times 2 becomes pi over 4, becomes root 2 over 2. So it's certainly going up like this, and coming in towards the origin. At pi over 6, times 2 would be pi over 3. Cosine of pi over 3 is a half. And now let's see, root 2 over 2, that was 0.707, so a half is actually getting lower. So coming in close. At, let's see, we did pi over 6, that became pi over 3. How about at pi over 4, times 2 is pi over 2. Cosine of pi over 2 is 0. So it actually comes in eventually to have radius 0. So I'll tell you what actually happens. If you keep graphing this, it goes like that. And if you'd gone the other way, it goes like that. But it doesn't stop there, right? It comes around, but when it gets to here, it actually goes like that, like that, and like that. Isn't that pretty? Okay, it's not. It actually should be the same, length. It's symmetric, certainly. Oh dear. Oh boy.
That's good.
Good enough. Okay, you can see it's like a 4-leaf clover. Okay, if you have a graphing calculator, there's a polar coordinate feature on it. You can put it into the polar mode, tell it r equals cosine 2 theta, it'll graph this. Okay? If you change this this coefficient, it'll change the number of leaves that you have. So you can make lots of leaves. You make that number really big, you'll see lots of leaves. You put sine in there, see what it does. There's lots of cool stuff. So let's say I want to integrate over this region, just one leaf of the clover. In fact, let's say I want to know what the area of that clover is. I want to know what the area is. Well, remember to compute the area over a region, so this is my D, I just integrate the function 1. Because what does that do? Well, that puts a surface of size, just a plane size 1 over the whole thing. And so when I compute the volume, it'll just be the area times 1, which is the area. So I want to compute this. Okay, so to do so, I need to write down D in a nice way. Let's see. I'm going to give things in terms of polar coordinates. Now let's see, we saw that to go from here, this started when we shook theta 0, and it ended at pi over 4. So when we multiplied by pi over 2 times pi over 4, you get pi over 2, cosine pi over 2 is 0. So this went from 0 to pi over 4. To get this side of it, you go from minus pi over 4 to 0. When you multiply by 2, with minus pi over 4, you get minus pi over 2. Of course, minus pi over 2 is also 0. So it turns out that to get the whole thing, you have to go from minus pi over 4 to pi over 4.
Just do 2 times 0 to
2 times.
You integrate the function. Just from
We
0
could.
to pi
We
over
could.
4
We could do that just from 0 to pi over 4. In this case, it won't really make a difference. But you're right. Because of the natural symmetry here, you could just integrate from 0 to pi over 4 and multiply your result by 2. That's true. Okay, so the angle that you choose to go around this part of the curve is minus pi over 4 and pi over 4. Now what's the radius? Well, the radius can go anywhere from 0 all the way to cosine of 2 pi. In that direction, right? You're not just getting the boundary, but you're getting everything in it. So the radius is never less than 0, but it's always greater than or equal to 0 and less than or equal to cosine of 2 theta. So to compute this double integral, which will give us the area of this clover, we simply need to apply the formula. We're going to do an iterated integral from minus pi over 4 to pi over 4. And then an integral from 0 to cosine of 2 theta. And then we integrate the function, but the function, well, it's just a constant function, 1. So there's no r cosine theta, no y cosine theta, because there's no x and y. I mean, I said r cosine theta, r sine theta. It's just a 1 here. So this is still a 1, but we still have to remember the r before the dr d theta. So that's what we need to compute. And this should be fairly routine now. So let's see. You integrate from minus pi over 4 to pi over 4. Integrate from 0 to cosine of 2 theta. R, dr, d theta. You get the integral from minus pi over 4 to pi over 4. And let's see, the integral of r is a half r squared. course, when I put in the 0 for r, it would die. So I'm just going to get a cosine squared. So minus pi over 4, a half. I can pull the half out. Cosine squared 2 theta. Okay, so remember there's we use integration by parts to compute cosine, the integral of cosine squared. The cosine of 2 theta, well, we can get rid of the 2 theta if we do a u substitution. And that u substitution is going to produce another half to come out front. So, just write it down. Just do a little side work here. Well, here, we'll do the u substitution. If we do the substitution u equals 2 theta, then du equals 2 d theta. Or if you like, d theta equals a half du. So if I want to replace my d theta, I just put a half du, and that will pull this another half out. So I get a fourth. Oh, and I guess I should replace my bounds too. Let's see, so if theta equals minus pi over 4, then u equals 2 times minus pi over 4, minus pi over 2. And if theta equals pi over 4, then u equals 2 times pi over 4, which is pi over 2. So this becomes minus pi over 2 to pi over 2 cosine squared u du. And I don't need to convert back at the end. I switched all the bounds into u's. Now we need to remember what cosine squared's antiderivative is. So we did this a couple weeks ago with sine squared. So we'll just do it. It's the same thing. You can use this tabular method. So you start with cosine of u, differentiate on the left, integrate on the right. So when you differentiate, you get minus sine. When you integrate, you get sine. And you can, in the tabular method, you're allowed to move things across without changing the problem. So I'll move the sine across, and I'll leave the minus 1. So I'll get minus 1, and I'll get sine squared. But I actually don't want to write it as sine squared. I want to write it as 1 minus cosine squared. Sine squared and 1 minus cosine squared, those are the same. And now I play the game again. I differentiate over here, and it becomes 0. And I integrate on this side. And if I call this original integral I, and when I integrate, I get u minus the integral of cosine squared, which is just I. So u minus I. Now I draw my lines into the box, out of the box, plus, minus. And so the answer is cosine of u, sine of u. Minus 1, so that's plus 1 times u, so plus u minus I. So then I'll add the I to the other side and get 2I, and then I'll divide by 2. And I'll get I equals a half u plus sine u cosine u. Okay, so I can use that result here. And I get a fourth, let's see, times a half. And then I get u plus sine u cosine u. And we'll evaluate at minus pi over 2 and pi over 2. So let's see. At pi over 2, We'll see, I always get an eighth out here. And pi over 2, I get pi over 2 plus, well, sine of pi over 2 is 1, but cosine of pi over 2 is 0. So that's just pi over 2. Minus, now at minus pi over 2, this becomes minus pi over 2. And again, cosine of minus pi over 2 is 0, so you don't get anything there. So pi over 2 minus pi over 2 is 2 pi's over 2. It's just pi over 8. Okay. So the area of this little clover leaf is pi over 8. Okay, I got it. So you see, we can't forget how to do basic integration. You have to remember how to do these things. Okay, any questions about this? The hardest part, I think, for you guys, other than remembering how to integrate, is setting up this D. Is that right? Looking, even if you, well, first you got to know how to graph this thing, you would think.
I got it. Yeah.
But even if you knew the graph, right, you have to think a little bit to be able to write down this region. This is where plotting points, normally I don't like to plot points so much, but here it helped a little bit to know, oh yeah, okay, I started at 0 and I went to pi over 4, and this is symmetric. It must be going from minus pi over 4 to 0 on this side. But you could plot points to see that as well. Okay. So there will be some homework problems. You can get some practice with that.
Is there some pattern with the integration of transformations of cosine, like just with the integer in front of theta? So the, like say the sums of each of the regions, like here we have 4, so if you add them all together, the area would be pi over 2. Is there a pattern?
Oh, is it that
like cosine of just theta, would it still, the sum of all the regions be pi over 2?
That's a really good question then. Well, let's see if we can just give a quick answer to that. So the bounds will change, of course, by, well, it's exactly given by this factor here. So normally, it would, if it was just a theta, then it would go from minus pi over 2 to pi over 2. If you multiply by 2, it divides it. So
basically what we did with the substitution.
Yeah, it'll become pi divided by 2n, and minus pi divided by 2n. This part stays the same when you're computing this area, and this, of course, becomes cosine of n theta. When you integrate, well, this is the same integration, but you're going to get cosine squared of n theta. So you would factor out, instead of having a, when you do a substitution, instead of having a 1 over 4, because that was a half times a half, you factor out a 1 over n, so it would be 1 over 2n. These will actually always become pi over 2 and minus pi over 2 when you do the substitution. And once you get to here, the integral is the same. So it would be 1 over 2n, and so it would be 1 over 4n, basically. And then this is going to be the same every time, pi. So it would be actually pi over 4n. So the general answer, so Ben's question is, if you made this an n theta, so you had more leaves, what would the area of each one of them be? And the answer is pi over 4n in general. And the number of leaves kind of goes up somehow with the n. And Ben's question is, if you add up all of the leaves, do you get a constant area? Is that right? Mm-hmm. So here it was pi over 8, and there's 4 of them, so there's pi over 2. Let's see. I think so. Because yeah, if you put a 4 up there, then I think you get 8 leaves, and so you pi over. Yeah. I'm pretty sure that's true.
You have to consider the
That's for
present.
even. What's that?
Minus. You have the positive sign and the negative sign.
Ah, remember, the positive and negative has to do with the function you're integrating, not the region you're integrating over. Right? For instance, if you're just integrating a function like this, when you're trying to integrate it, let's say it even goes up. What's important is not that over here your A's and B, I mean here an A is negative or something, right? What's important is where's the function? Is it positive? Is the function negative? Right? The values of A and B, those are not so relevant. It's only the function value. For this, when you integrate, well, the function is 1. It's always positive. The fact that these happen to go into what we consider the negative axis has nothing to do with it. We're not even in, I mean, if you like, we're not in the rectangular coordinate system. Right? We're in the polar coordinate system. So the region itself, that doesn't have anything to do with it. Because you could just change, you could forget that there's even a cross here. You just have some picture in the middle of the thing and say, okay, I have that picture, I want to integrate over it. Right? So then all that matters is the value of the function over that region. Okay. All right. All right, so you get some practice on this. Have some fun with that. So now I want to talk about how we can use what we just learned about how to convert things into polar coordinates to solve problems with triple integrals with cylindrical coordinates without actually having to learn really anything new. I have to draw a picture that I have to look at. There's just too many lines on it. So now we're going to transition to cylindrical coordinates. So here's the picture. And in cylindrical coordinates, well, normally I like to draw domains down here, and I still want to do that, but they have to, I want them to look like a polar rectangle, so it's got to look something like that. So this would be my polar rectangle. So we'll call this here, this is the angle alpha, and that's the angle beta. And I'll bound R here by, these should be coming out. R is going to be bounded by two functions of theta. So this is a type theta region. Okay, so this is on the xy plane. And now I want to put a solid above it. So to do that, I think I typically want to draw little lines going up. Okay, so let's see if we can do this reasonably well. So come down this way. That. Get that down a little bit. Okay, this is the bottom of the piece. I haven't got to the top yet. Okay, and then we'll make this go up. This go up.
Just go up.
That go up. That go back there. All right, so there is a solid piece here. You can all see that there's this little piece of cheese up there?
Yeah.
Okay, and it's sitting, okay, I know this is not looking good. It's sitting above this region, right? If you project down, it should go onto this region. That's what these little lines going up are supposed to represent. I apologize that I can't draw this much better. If you were looking straight down from above this, you shouldn't be able to see the domain below it, right? Because it shouldn't go out any further than it. Right? If you took any point in here and went straight down, it should end up in that region.
So it would be that region with the height, that's what it is?
Yeah, so it's this part here. This is that's the piece of cheese sitting above it. Maybe this is a tumor or something, somebody's body. You give me a weird look like that. Where do you think why do we care about analyzing, for instance, three-dimensional objects? Well, some of us want to cure cancer.
Okay.
Okay, and I'll say you want to cure cancer. Well, you have to model what tumors look like. And what does a tumor look like? Well, I don't know really what a tumor looks like. But I do know that it's three-dimensional and that they're reasonably symmetric. At least it's not a bad model to model them in a symmetric way. And so, okay, so it's important.
So you draw a cube.
Yeah, but they're not cubic. I mean,
How do you know? You said you didn't know what they looked like.
I know that's not what they model. The cubes would not be a very good. This would not be good. Okay, so now let me call the name. This top surface is going to be given by a function, say of x and y, and the bottom surface will be given by a function. Okay. And so if I call this region E, then E, I'll call this bottom region D. Then E is given as all points x, y, z, where x and y, those actually, if you forget the z coordinate, they just land in D, right? That's what I was saying, there's the projection. Forget the z coordinate, it's in D. And z should sit between this function u1 of xy and u2 of xy. Okay? So this is a type xy region because the z coordinate is given as sitting between two functions of x and y. Okay, and then what about this d? Well, we know what this d is given by. It's a type theta region. Right? Theta goes between alpha and beta. It's all r theta, such that alpha is less than or equal to theta is less than or equal to beta, and r sits between h1 and h2. Okay. Okay, so let's assume that I have a continuous function. That way, all my integrals will exist. And I want to integrate f over e. So we've already seen before, you can turn this into a double integral over d, where you then integrate between u1 of xy to u2 of xy, and then you integrate the function dz, and then you integrate dA. Okay, good. So if we want to transition, though, for instance, maybe this function, when we go to integrate it, is not going to be nice. Like it has a square root of x squared plus y squared in it. Something that we don't want to have to integrate. And so we decide, well, if this was a two-dimensional integral, I'd want to turn it into polar coordinates, for instance. Okay, well, we're going to turn this into cylindrical coordinates. And the way we do it is almost exactly the same, only now we have three things to worry about. So this, continuing on, we can rewrite this as, well, first, the D region, if I want to integrate over that, this tells me what my bounds should be. I first integrate from alpha to beta. I then integrate from h1 of theta to h2 of theta. And then, when I go on the inside, I'm supposed to be integrating u1 of xy to u2 of xy. But I'm making the conversion to cylindrical coordinates. So remember, when you do cylindrical coordinates, if you have x, y, z, and you want to turn this into r, theta, z, then you just use the polar coordinate rules. R equals, what's the R? The R is given by r squared equals x squared plus y squared. X equals r cosine theta. Y equals r sine theta. And how do you convert z? Well, z just goes to z. Right. If you need theta, tangent of theta is y over x. I feel like we've written these down today somewhere.
Mm-hmm.
Okay. So it's just like the polar coordinates. I mean, these are exactly the polar coordinate conditions, and then the cylindrical coordinate condition is just z equals z. Nothing happens. So, if I want to convert this, well, instead of looking at u1 of xy, I need to do u1 of r cosine theta, comma r sine theta. I need to convert everything into polar. And u2, but I still haven't found what I'm looking for.
What?
u2.
Oh.
Oh, so young. Okay, and then my f, which was originally given in terms of x, y, and z, that I convert into cylindrical form. So this is f of r cosine theta, r sine theta, and then what happens to z? Well, z stays itself. And then I need to do what? First is my dz. Oh, and I need an r because I switched to polar form. dz, then dr, then d theta. Okay, so this is the formula when you put things into cylindrical coordinates. You should not memorize this. If you memorize this, your brain might explode, right? You want to remember this in pieces. You want to remember that when you convert from rectangular to polar coordinates, that you use x equals r cosine theta, y equals r sine theta. Okay, you have to remember that. That way you can just plug these in. You don't have to remember this whole thing. Just remember that. You take your x's, turn them into r cosines, your y's turn them into r sines. Z's stay the same. Whenever you change to polar or cylindrical, you gotta get an r just shows up. You have to remember these. Add an r. Okay? And then the order of these things is reasonably natural. You're doing your z's first, right? Because you want to end up integrating over this double integral region, right? Over this d. Okay, which is just has to do with the r and the theta, not the z. Okay? And then the way you remember which one goes between the r and the theta. Well, this is a type theta region. That means that the theta is where it's actually given between two numbers. And whenever it's given between two numbers, that's got to be the first integral you see. Okay? If it's given by functions, that should be later down the road. Okay? So all the functions need to be on the inside. So you have the r cosines, then the r thetas, then just the thetas, and then there's no functions at all. So there should be less in the function. Here you had both r and theta. Here you had just theta. You got rid of the r. That means it's r's turn. And then you got rid of the theta, so that means it's theta's turn. You see what I mean by that? The first time you do it with respect to z, so there's no z in here, so it must be z's turn. Then you got rid of the r, so it must be r's turn. And then you got rid of the theta, so it must be theta's turn. Don't try to memorize it all at once. You just keep writing these things down when you see the actual problem. Okay, so let's do an example, just to see if this be done. So, oh, I thought somebody said, oh. Okay, so let me give you kind of a tricky problem. Alright, so we've ended up with this integral somehow. A lovely triple integral. Well, it's actually an iterated integral. But of course, we know it's coming from a triple integral. And, well, the first time that we go to integrate this, it's not going to be a problem because you're just doing it with respect to z. There's no z's in here, so that's easy. But then when you put the z in, let's see what you're going to get. Well, you get two of those, and then you'll subtract this thing times that. And now you're going to have to integrate with respect to y, and you're going to have an x squared plus y squared times the square root of x squared plus y squared. And all of a sudden this is looking, quite bad, yeah? And you're not wanting to do this. And I don't blame you. I wouldn't want to do it either. So we decided, well, maybe we should do a coordinate system change. Maybe this will be easier, right? It looks like it's got an x squared plus y squared. That usually is a good sign. Right? Good idea, we should do something like that. All right, so let's give it a try. Well, to do that, it's very helpful if you know what this thing looks like, if you can figure out what the region really is. Well, we know, of course, we can write down this. E is given by x, y, z, where, we'll see, the x goes from -2 to 2. The y goes from minus root 4 minus x squared to plus root 4 minus x squared. And the z goes between x squared plus y squared square rooted and 2. Okay, so I just copied that off of the integrals. So you don't need to draw a picture of this, but I will just, so maybe we get some sense of what's going on. I think I'll go 3 dimensions here. So the x is going between -2 and 2. So 1, 2, 1, 2, fine. And then y, once you know what the x is, y goes between the square root of 4 minus x squared and minus square root of 4 minus x squared. So that's living on the xy plane. What does that look like?
Circle.
Yeah, it's a circle, right? Remember, x squared plus y squared equals 4 would be a circle of radius 2. If you solve for y, you'd get y equals plus or minus the square root of 4 minus x squared. So this is the minus, and that's the plus part. So this is actually just going to be, wait a second. This should be flat, really. This is on the xy plane. That's a little too circular. It actually should be better. Okay, so this is the projection. Whatever this region is, if you project down to the xy axis, it looks like a circle of radius 2. Now, what are the z values? Well, let's see, it's always less than 2. So I can go up here to 2. And it's going to be less than or equal to that. But it's always bigger than x squared plus y squared square rooted, which is always at least 0. So it's sitting between 0 and 2. And, well, let's see, if the square root of x squared plus y squared, well, this is just a circle of radius r squared, and square root, you just get a circle of radius r. So if the radius is 0, which would be right here, then it goes all the way up to 2. Okay? But as you go out further, the radius gets bigger. Z is only allowed to be as no smaller than the radius. So as the radius gets bigger, z can only go between something bigger and 2. So when you get all the way to, we'll see, out to 2, right, on the thing, it can only be up at 2. The same thing over like here. So in fact, what this has to look like is a cone, because what's happening, right, as the radius gets bigger, z can only, it has to get bigger and bigger, right? Z can't be too low. It has to always be bigger than the radius. So it's actually this cone here. Okay, fine. And the projection of this cone should be this circle. Okay, so now let's try to rewrite this in terms of polar coordinates. So in polar coordinates, things look like r theta z. And let's see here. Well, things shouldn't be so bad. The theta, remember the theta is what's happening on the, it's the angle on the xy plane. And that goes all the way around. So the theta is going between 0 and 2 pi. The radius, okay, good, that's fine. At any given theta, the radius can go all the way from 0 all the way out to 2. Right? That's what this circle says. You can go all the way out to 2. So the radius is going between 0 and 2. The theta is going between 0 and 2 pi. Okay, this is just telling you the circle of radius 2. Then the question is, what's the z-coordinate? And the z-coordinate is exactly the same z-coordinate as we had before. But we don't want to write it like this, because this has x's and y's, and we just want r's and thetas. But how do you write this in terms of r's and thetas? Yeah, square root of r squared, right? X squared plus y squared is r squared. Then you take the square root and you get r. So the z, the way to write the z is just it's bigger than r and it's less than or equal to 2. Now this is a much nicer looking region, don't you think, than this? Just aesthetically. Now let's see if the computation of the integral gets any easier.
Could you explain again how do you get r?
Between 0 and 2. Well, remember, if you forget about the z-coordinate, then it just should be whatever the projection is onto the xy plane. In the xy plane, the projection is a circle of radius 2. So you should be getting everything between 0 and 2 for your radius. This cone, if you look at all the points in this cone, they're all coming from thetas between 0 and 2 pi and r's between 0 and 2. The only thing that's making this into a cone is that the z-coordinate changes based on the radius. Right? But the radius can go anywhere between 0 and 2. So think here, z can go between 0 and 2 all the way up to between 2 and 2. And that's exactly what's happening. Down here, the z can go between 0 and 2. Out here, when the radius is bigger, it can only go between 2 and 2. Right? It can't go anywhere. It's just a flat circle. But over here, you can have this piece, and the radius is r there, or here, you have this much z. And at 1, it can have all the way up to, well, the radius is 0, go all the way up to 2. Okay. So let's rewrite the integral. So let me call it I, just so we can write I equals. So I equals, so we'll integrate, well, it doesn't matter here if we do the r and the theta first, because this is better than type theta region. Both of them are given in terms of constants. So we'll say we'll do the, we'll still do the thetas first, just for fun. Okay, and then we'll do, say, 0 to 2,
Yeah.
and then we'll integrate from r to 2. And then we have our function, and our function was x squared plus y squared, which is just r squared. So it becomes an r squared, but remember we're converting to polar coordinates or cylindrical coordinates, and the cost of doing business when you change the integral is what? You have to add an extra r, right? It's just a cost of doing business. Okay, and then this is the z, this is the r, and this is the theta.
Can you, really quickly, the difference between polar and cylindrical coordinates?
The z,
Just the, okay.
that's the only difference, right?
But they could,
The
they're converted the
transformation
same.
laws are the same,
Okay.
except for the z, right? In the cylindrical coordinates, you get this z equals z.
If you think of polar as circle coordinates and cylindrical just means
Exactly. That's why I love that circle coordinate name. Circles and then cylindrical, you add the z.
Okay.
Okay. Now, while we're at this juncture, something in here, let me just quickly write this. Right, this thing is coming from the z's, this is coming from the r's, and this is coming from the thetas. You can see that this integral is going to be a heck of a lot easier to compute. This one we had basically no hope. This one should be quite nice. And I want to use, to write this down in a quicker way, I want to use this product rule that we showed a while back. So remember, the product rule for integrals in single variable calculus does not hold. The integral of a product is not the product of the integrals. However, in multivariable, we have something which is like the product rule. If you have a product of two functions, one is purely a function of x and one is purely a function of y, then you can break it up into two integrals, an integral with respect to x and an integral with respect to y, and multiply them. So here, I have a function, r cubed, which is a function just of r. And then if you like, I have a function 1, which is a function of z, and a function 1, which is a function of theta, all multiplied. So actually you can break this up into three separate integrals using our sort of abbreviated rule. So let's see, we'll do the theta one first. So the theta becomes integral 0 to 2 pi, just d theta. There's no theta in there, so you can pull it out. Then this one, the r, is integral from 0 to 2 of r cubed, dr. And then the last one is integral from, let's see, our z, so r to 2 of dz. Okay, because there's no z's in here. And this will make things a little easier to compute. Because, let's see, this first one, and if you don't like the way I thought about this in terms of product rules, just think, you can, this r with respect to z is a constant. So you could pull it out of this integral, and then you'd be integrating first r to 2 dz. That's exactly what this is. And then the next thing you'd be doing is, well, whatever you get from this is going to, oh, there's a problem, isn't there? Yeah, what's the problem? The problem is this will introduce an r into things. Okay, so we can't quite be that fast, right? We have to leave those first two together. We can pull this one out, because you can't ever get a theta from any of this stuff. But we have to be careful. Okay, so we will have to, can't quite do that the way we wanted to. Okay, so this is r cubed dz dr. Okay, so we can do this. It's still the case that we can pull this r cubed out. That still is true, because it is a constant with respect to z. Okay, so now this first bit, when you integrate over the function 1, it's just telling you the length of the interval, which is 2 pi. Times 2 pi times, okay, we're going to integrate from 0 to 2 r cubed times, well, the length of this interval is just 2 minus r dr. Okay, so this is 2r cubed minus r to the 4th. So this will be 1/2 r to the 4th minus 1/5 r to the 5th of evaluated at 0 and 2. Let's see, when you put it in 0, it dies, so you just need to evaluate at 2. So that's 16 over 2 is 8. And 32 over 5. And let's see, well, that's 40 over 5 minus 32 over 5 is 8 over 5. Times 2 pi is 16 over 5 pi. The important part is, of course, okay, you know how to compute an iterated integral. You've had some practice doing that. And this is a particularly easy one to do, right? There's really, it just comes down to the power rule. Nothing interesting going on there. But this one was nearly impossible for you guys to do. Yeah? And just a slick, and I'm not, when I say you guys, I don't just mean you. I mean, I would certainly struggle doing this one without doing a coordinate change. So you can see though the value of doing that. This is a terribly, I mean, this shouldn't be that hard a problem, is it? I mean, this is just a nice cone. That's a reasonable geometric object. You know? But the formulas are so complicated that we just don't have any idea how to do it that way. But this way, everything becomes really simple. So this is a good idea. Okay. Questions? Let's see. What should I point out about this? First, you didn't really need to draw this picture to solve the problem. I think it's sometimes very helpful to see a picture of it. You could have just said, well, these two conditions right here are giving me a circle, and it's a circle with radius 2. Right? So that means that my xy, on the xy plane, the polar coordinates are going to be a circle of radius 2. And there's the way you draw a circle of radius 2 in polar coordinates is you let the radius, well, if you want a disk really, if you let the radius run between 0 and the radius of the circle you want. Let theta go all the way around. And then to get the z, well, the way we did is we just plugged in our polar coordinate changes into this. So there we go. And then we can evaluate. So you didn't really need to draw a picture for it. You just need to have some intuition and some sense of how do figures that are normally have complicated formulas in rectangular coordinates, how do you write those in polar coordinates? And with things like circles, they're much easier, or sectors of circles. Okay, well, let's start the last bit, which is doing triple integrals with spherical coordinates. Okay, so somehow cylindrical coordinates was too easy. It was like cheating. Right? Once you got polar coordinates and you learned how to transition from the two-dimensional rectangular system to the polar system, going to cylindrical coordinates, you just add a z. Everything basically stays the same. So this was like cheating. Spherical coordinates, you actually have to do a little bit of work. I'm not going to show you all of the work because in some sense it's just too much repetition. You remember how we computed a rectangular, a single variable integral, right, over just rectangular coordinates. We broke up the region into rectangles, added up the area, and that gave us an approximation. We took a limit, we got the integral. Yeah? And then when we did polar, we used polar rectangles, and we had to draw these nice pictures, and they were now curved rectangles. But again, what we did is we added up a bunch of them, and took the limit, and we got the double integral. Right? So the same thing is going to happen to do these spherical coordinate systems and the triple integrals. And all you're going to be doing there is because you're in a 3D land, you're going to be taking some region and breaking it up into little, normally if it was rectangular, into little cubes. Right? That's what we did for the triple integral. And then we take the limit and add, after we add them all up. But now we're going to use spherical cubes. Whatever that means, right? Okay, well it should be a cube, right, where there's some curvature to it based on the fact that you're now in spherical coordinates. Okay, and you take the limit after you take the sum and blah, blah, blah. Okay, it works in exactly the same way. What I'll do is I'll give you the formula. What we saw last time when you switched from rectangular to polar coordinates for a double integral is you introduced this extra r. And that r came from like the formula 2 pi r. I'm sorry, from pi r squared, actually. So when we do the spherical one, we're going to introduce a little bit more than just an extra r. There's actually going to be, well, it'll be a little more complicated. So before we do it, it's probably good if I just remind you what the spherical coordinate system is, since I imagine it may have left your brain since we did it last week. So you take a point and we'll connect a ray from the origin to that point. And this point is going to be given a spherical coordinate that looks like, remember this is rho, theta, and then phi. And rho, remember, was the length of this line segment going from the origin to the point. Now, where does this theta come from? Well, this theta is actually the same theta as you had in polar coordinates. So if I project this down to the xy plane, then I can look at the theta that I get between the x-axis and this line segment. And that's the theta that I choose here. And then the phi is going to be the angle between this line segment and the z-axis. So this was the spherical system. And let me remind you how to convert between something. So if you have x, y, z, and you want to convert into rho, theta, phi, the rho squared, remember the rho squared, the reason why these are called spherical coordinates, right, is you think of a sphere, and this point is sitting on a sphere. So this is just the radius of the sphere. So it's given by just squaring and summing the x, y, and z coordinates. Just like a circle is given by x squared equals y squared equals r squared, a sphere is given by x squared equals y squared equals z squared equals rho squared. There's a couple ways that you could compute this theta, but the way I'll write down for this one, because it's quite useful, is the cosine of theta, so this angle. I'm going to give that in terms of, something seems funny there. Yeah, made a mistake in my notes. So it's given by x over rho times sine phi. Okay, well this isn't helpful unless you know what phi is. But phi you can get by taking, well, the cosine of phi is going to be z divided by rho. And if you want to go the other way, if you have rho theta phi, and you want to go to x, y, z, then the x, well, we can actually see it from over here. X is rho sine of phi cosine of theta. We don't have it up here, but we could have. The y is given by rho sine of phi sine of theta. And the z, well, that again is given by this formula, is rho cosine of phi. So, we remember we had this convention that we assume that our rho is always going to be non-negative, and that our phi rather, is going to be between 0 and pi. And this will, for our purposes, give us a unique way to represent every point. Okay, so we're running out of time here, so let me just write down quickly what we did. So, in polar coordinates, we took rectangles, and all right, that was the object that we wanted to integrate over, and we turned it into these polar rectangles. And that's what we wanted to integrate over for polar stuff. In spherical, we're going to take the cubes from rectangulars, and we don't want to integrate over those anymore. We want to integrate over the spherical rectangles, and those might look like, well, I have a really nice picture here. I'll see if I can faithfully reproduce it. Some sort of curved shape, right, coming from a sphere. And what this should be is actually, well, what did it mean that I had a rectangle here? It meant that I had 3 coordinates, x, y, and z, and they were both given as intervals. I mean, all given as intervals. So x went between a and b, y went between c and d, and z went between e and f. Here, since things are going to be given in terms of rho, theta, and phi, I want all 3 of these to be given by numbers. So rho goes between a and b, theta goes between alpha and beta, and phi goes between c and d, say. So this is what I mean by a spherical rectangle. They're all given by numbers. None of them is given as a function of the other ones. And it's just an interval cross an interval cross an interval. So this will be the nice region that we want to integrate over in spherical coordinates. Okay. So tomorrow we'll start by writing down the formula for how to change a triple integral into one in rectangular coordinates into one with spherical coordinates. And we'll see we have to add a little more than just an r. It's a little more complicated.